On November 26, Morphisec prevented a then unknown ransomware attack, successfully protecting a customer with over 10,000 endpoints and servers. While the ransomware successfully bypassed the leading next-gen AV and EPP solutions installed by the customer, Morphisec was installed in parallel and thwarted the attack. Over the next 12 minutes, Nadav Lorber, Security Research Team Lead, and Oren Voskin, Product Marketing Director, will get you up to speed on this previously unidentified variant of the Babuk Ransomware, how Morphisec detected and prevented the attack, and much, much more.
Hello, everyone, and I hope you can all hear me well. My name is Oren Voskin. I'm the Product Marketing Director at Morphisec, and I'm really thrilled to be joined by Nadav Lorber, our Security Research Team Lead. Now, we're here together today to talk about a significant new research. So on Saturday, November 26th, Morphisec was notified. We received an alert from our customer, a high priority alert. We analyzed that alert and found out that we've been able to prevent a new string, a new variant of the Babuk ransomware, so a new variant that was previously unseen, and this webinar is dedicated for that analysis. So a few words about the attack and what happened. So our customer, the Morphisec customer, is a multinational manufacturing company, quite large scale, of over 10,000 endpoints and systems and servers. The ransomware evaded the endpoint security solutions used by the customer, a next-gen AV and an endpoint protection solution. And Morphisec was able to prevent the attack with our moving target defense technology. And Morphisec also observed that the attack, even after it was published on threat analytics platforms like VirusTotal, continued to evade leading EDRs for nearly 2 weeks. It took a while to catch up. Morphisec was also hired to provide incident response services to the customer. So this limits our scope in this session to talk about a technical analysis of the ransomware. So with that, I'll hand it over to Nadav.
Hi, everyone. So we will now begin with kind of an overview of the attack flow. We'll start from the point that the attacker, that the threat actor actually already obtained the domain admin. So the attacker initiated the attack from the Active Directory. He hosted on the NELT logon shared folder 2 files. One of them is ims.bat, which is the first file in the infection, and the Sapphire ims.msi, which is an MSI executable that was used in a later on stage. This was delivered over a 24 hours period to many thousands of endpoints and servers. So the attack executed on each of the victims by utilizing a vulnerable Microsoft executable, which is a debugger that we'll see later on, and name it as a Sapphire MS client. This vulnerable application is vulnerable to side loading or search order hijacking technique. The attacker utilized it with a DLL that's called dbg.tng. This DLL was delivered with 2 additional files, encrypted files. One of them is the shellcode, which is used as a reflective loader to load within the memory the ransomware payload. And once it loads the ransomware executes and encrypts the system. So we'll start with the first stage, which is the attack delivery, the IMS BAT that we spoke on. So it starts with setting up some UAC bypass within the registry, something that we see common in APTs. Then it does something that is pretty rare to see, and it checks for security solutions, and if it found the security solutions, it blocks the communication to them by adding a firewall rules. This can be resulted in alerts that are not going out from the system to the monitoring. And also many securities solutions today are based on cloud security. detection, and this can also avoid cloud detection solution by using that. After that, it execute the MSI installer that we saw that is stored on the network shell. The MSI installer then extract an exe DLL and the two encrypted file, which are named with a OCS extension, to the following folder within the host. You see user public. And eventually, it will execute the Cepher IMS client exe, which is the legitimate Windows application, with the two OCS file as parameters. You can also note that the MSI installer, when it was uploaded at one time to VirusTotal after the attack, and it got only one detection. So here I will dive a bit more into the actual loader and the reflective shellcode that is used to load the ransomware. So at the top, you can see the command line, the CMD command line that was sent to the computer to execute in order to run the attack. It runs the executable with the two OCS files as parameters. So as you can see, the executable is a legitimate Microsoft executable, which is a symbolic debugger for Windows. And it's a legitimate tool that is vulnerable to DLL side loading. The attacker drops the malicious DLL in the same directory, as you can see, which is the dbg-ng.dll, which then loads OCS, the OCS files in memory, both of them. It starts with decrypting the cell code and adjusts the memory protection, and also decrypts the ransomware itself in order to load it using the reflective shellcode. It's interesting also to note that we have seen this attack, this threat actor used in older attacks. In older attacks, he also utilized legitimate Windows Microsoft binaries. So he also used the legitimate executable binaries, and we assume that is strong. The threat actor really like using legitimate Microsoft applications, since they are more, they are less scanned by machine learning, scanner-based, and etc. Because most of the time those executions are legitimate. So once the cell code is running, it's used solely as a reflective loader that eventually load the ransomware within the memory. Here we can see that the very similarity between the code that the attacker used to open source projects. So when we analyze the attack, we've came across a very common pattern in all of the attack stages. This pattern that we noticed is that the attacker really prefer to use like open source code that is available on GitHub and modify it so it will not be detected or will not be recognized in order to try and do classification for the threat actor or correlation to other attacks. So we can see that the dbg-ng-dll is very similar to some payloader library, and the cell code is also very similar to another one. Here you can see side by side the Babuk that used in the attack and the decompiled code from the attack, and also the leak from the source code. We can see here that there are several similarities. The code structure, so the overall execution flow and the code structure really correlates to the Babuk. And also it's using the same encryption routine. One of the most characterizing function of any ransomware is the encryption routine. It's using the same one. And also the configuration that is provided to the ransomware is very, very similar. We saw some modification. The most recognized modification that we saw is that the attacker added a shadow copy deletion routine since the original source code that used by Babuk was not implementing that. The attacker chose to implement it, and it's also worth noting that also malware and ransomware such as Black Matter and Conti ransomware did this, doing the same behavior with deleting the shadow copy. So, summarizing it, we can see, as I said, across all the chain using the open source code, which is very interesting. We don't see it in many attacks that all of the chain is based on open source code. This is something that really expands the potential for the evasion techniques for the attacker, and also it's much more how to attribute this attack to a specific threat actor or country or etc. Generally, it's very challenging to get some visibility into runtime because EDR, XDR, etc. are usually restricted to use hooking or event tracing for Windows. And combining the threat actor by using a combination of different evasion techniques, it was successful with bypassing many security solutions that we have saw in our analysis. So it's clear to see that the threat actor know the weaknesses of monitoring and the scanning solutions in order to bypass them.
I mentioned before we promote industry-wide collaboration. We do have analytics that we share with vendors. We always welcome other EDR vendors to collaborate with us and share results of our findings, and hope to expand that in the future. So with that, I think this has been an exciting session. Thank you very much, Nadav. Please follow us on our social media and other venues, because we will be having a follow-up session with a more deeper end-to-end analysis of this incident. So thank you very much, everyone, and have a happy holidays.